Okay, thank you Abhijit for the invitation and happy to be back in TIFR after a year. This is the time I come here always and it's a nice place to be. Okay, so today I will be talking about action principle in conformal supergravity. In the previous two instances I talked about n equal to 4 supergravity and we used some formalism in the construction of action in n equal to 4 supergravity, which I did not discuss quite in details during those talks, which I am going to do today, and I will be discussing how to use it in the context of n equal to 2 supergravity to construct new kind of actions. So, this is based on two upcoming papers with these people, and yeah. So, the plan of the talk is I will give an introduction, a very brief introduction to conformal supergravity. I will discuss about a kind of invariant action for the chiral multiplet in n equal to 2 conformal supergravity, which is also known as the n equal to 2 chiral density formula. This is a kind of master action that we use to construct any kind of actions containing any kind of multiplets in n equal to 2 supergravity. So, basically what you have to do is you take any n equal to 2 multiplet and you try to embed it into the chiral multiplet, use this density formula and you get an invariant action containing those multiplets. Then I will go to a more generic action principle, which I call the super form action principle, from which one can derive this n equal to 2 chiral density formula and can obtain more generic actions that we do not get from the n equal to 2 chiral density formula. And I will show that one can obtain n equal to 2 chiral density formula from this action principle, and I will also show how to obtain a new density formula in n equal to 2 conformal supergravity, and we will use this new density formula to construct invariant action for what I call as a real scalar multiplet, and after imposing certain restrictions on this real scalar multiplet we get the tensor multiplet. So, one can obtain this using this new density formula, one can obtain new invariant action for the n equal to 2 tensor multiplet, which is the main result of this talk, and then I will conclude with some future directions. Okay, so yeah, so what is conformal supergravity? So, it is basically a theory of gravity which is invariant under the local symmetries associated with this superalgebra SU2,2/n, where n is the number of supersymmetries that you allow. If it is n equal to 2, then it is SU2,2/2. If it is n equal to 4, then it is SU2,2/4. So, so the idea is to start with the gauge theory for the superconformal algebra. Just SU2,2, just you take the conformal algebra and you start with the gauge theory of the conformal algebra, and then you impose, I mean, constraints and things like. I mean, basically in the end you will, that will be basically just the Wild square term that you get in conformal gravity. Yeah. So, basically what you do is you start with this gauge theory of the superconformal algebra, and by starting with the gauge theory I mean that you take all the generators of this algebra and you associate a gauge field for each of these generators, and then from the structure constants of the algebra you can write down the gauge symmetries of these gauge fields, you can write down curvatures associated with these gauge fields and so on. But then it is just a gauge theory that you have begin with, and the commutator of transformations that will close, let us say you take commutator of two supersymmetries, it will close to translation. Okay. But in a theory of gravity you would like that the commutator of supersymmetries close to a general coordinate transformation rather than a translation. So, in order to achieve that, in order to convert this translation, local translation to general coordinate transformation, you impose certain constraints. And by imposing these constraints, what you do is a set of the gauge fields of the superconformal algebra starts becoming dependent. For example, you impose one of the constraint, which is the curvature associated with local translation to 0. Okay. So, the local translation is PA and the corresponding gauge field is E mu A. Okay. And you can write down the curvature based on the how this gauge field, what are the gauge transformation of this gauge field, you can write down the curvature and you can write on the so you can write on the curvature associated with this translation. So, one of the constraints that you impose is that this curvature is 0, okay, and that basically makes the gauge field omega mu A B, which corresponds to local Lorentz transformation. This starts depending on the other gauge field, E psi. Psi is the gravitino, which is associated with the supersymmetry. Okay. Okay, so, by imposing this constraint, your gauge field associated with the local Lorentz transformation will depend on the other gauge fields, and you will start interpreting it as the spin connection. Similarly, you will have in order to convert the local translation to general coordinate transformation. So, you okay, that's a little involved. So, that I need to give a lecture on conformal gravity as a whole to do that. Okay. So, and similarly, you will see that the other constraints that you need to impose are, you take the curvature associated with local Lorentz transformation and you contract it with the inverse. So, after imposing this constraint, you start interpreting this as a Weyl-Bien, which also has an inverse, and then impose this constraint on the curvature associated with the local Lorentz transformation, and this makes the F mu A, which is a gauge field corresponding to spatial conformal transformation, that starts becoming a dependent gauge field.
What was that previous constraint?
This was the curvature associated with the local translation that is set to 0, and that can be algebraically solved, and this gauge field associated with the local Lorentz transformation becomes dependent on the other gauge fields. Similarly, this is also one of the constraints that you would like to impose, and that makes the gauge field associated with spatial conformal transformation dependent on the other gauge field. And you will also have a Fermi constraint, which is you take the curvature associated with the supersymmetry, with the Q supersymmetry. There are two kinds of supersymmetry in this superconformal algebra. One is the Q supersymmetry and the other is the S supersymmetry. So, you take the curvature associated with the Q supersymmetry and you contract it with gamma mu and set it equal to 0. Okay. And this basically makes the gauge field associated with the S supersymmetry dependent on the other gauge fields, on the independent gauge fields. So, this set of gauge fields omega mu A B, the F mu A and phi mu I, they become dependent gauge fields by imposing these constraints, and after imposing these constraints, your commutator of two supersymmetries, instead of closing on to translation, it closes to general coordinate transformation, and what you get is a theory of gravity instead of a gauge theory.
So, gauge theory to begin with is not general coordinate.
Yeah, it's a gauge theory, it's an intern. So, basically you have all the superconformal algebra, you have all the generators and you write down a gauge theory based on that. So, there is no general coordinate transformation, it's just internal symmetries. Okay, and you make this, you realize this translation as a general coordinate transformation after imposing this set of constraints. Yeah.
And you don't assume that all this is happening in flat space?
No.
It can be an any four-dimensional.
Yeah, right. Okay.
How does one know which constraints to impose?
Okay, so as I said, these constraints are not not very sacred constraint. You can change this constraint by some covariant terms. For example, typically in n equal to 2, what people do is not impose this constraint, but they add some covariant terms to this and set that equal to 0. So, what that basically does is that basically means that you are making some sort of field redefinition to F mu A coming from these covariant terms. So, you can so you need to impose some constraints and the number of constraints is as many as, I mean, this fields has to be dependent, but what constraints you impose is not very well defined, and depending on the problem and how you want to simplify it, you could impose you could modify these constraints, right. So, that basically means you make some field definition to these dependent gauge fields by some covariant terms. Okay. So, yeah, I mean this thing, I mean I don't have I don't have this thing to show you, but this thing comes from demanding that your commutator of supersymmetry is actually closest to general coordinate transformation and not translation. And then if you yeah, and these things will also follow from similar, like you have this you what you do is basically you look at the how translation acts on Wheelbane and how translation acts on this gauge field and how general coordinate transformation acts on this gauge field, and from there you sort of see that if you impose this constraint, then they are actually the same, translation and general coordinate transformation. These things also would appear when you look at it, look at some other gauge fields. But then, as I said, instead of this, it can be some combination of some covariant terms along with this that can be also set to 0, and that will still work. Okay. With dilatation, that is not a dependent gauge field, that will be an independent gauge field. Yeah. So, your independent gauge fields are basically E mu A, that is the gauge field corresponding to translation, which will be now interpreted as the Wheelbane after imposing these constraints, and then you have the gauge field associated with the dilatation, and you will have gauge field associated with the R symmetry. So, if you have n equal to 2 supergravity, you have SU2 cross E1 R symmetry. So, you will have gauge field associated with the SU2 R symmetry and the E1 R symmetry. So, these will be the independent bosonic gauge fields, and you will have independent Fermi gauge field, which is the gravitino, and the other Fermi gauge field, which is associated with the S supersymmetry, that will be dependent. Yeah, but no, yeah. Yeah, so that will be another. Yeah, so I'll come to that. I'm not necessarily. I mean, not really. I will tell you in a moment. So if you look at these gauge fields, the independent gauge fields, and basically if you count the number of components, basically by counting the number of components, mean you directly count the number of components of these gauge fields, and you subtract the number of symmetries from that, you will see that the number of bosonic off-shell components and the fermionic off-shell components, they don't match. Okay. So, for example, if you see this in 4 dimension, this is just 4 into 4 16, this is 4, this is 4 into 3 12, and this is 4, right. So, this is just naive counting the number of components, and then you have the symmetries. So, diffeomorphism you have 4, local Lorentz transformation you have 6, dilatation you have 1, SU2 you have 3, and E1 you have 1. So, that is basically 6, 4, 10, 11, 14, 15. Okay. So, if you subtract, basically what you get is 16 plus 4, 20, 32, 36 minus 15 is 21. You get here, yeah, 21, and here if you see, this is 4 into 2, this is 2, 4 into 2, and each of them is 4 components. So, that is 32, and number of supersymmetry is basically 2 into 4, that is equal to 8. Okay. Supersymmetry parameter is epsilon I, so that is 2 into 4 is equal to 8. So, 32 minus 8, you get 24. Okay. So, 21 bosonic components and 24 fermionic components is what you get from the counting of the off-shell degrees of freedom for these gauge fields. Okay. So, clearly there is a mismatch between the number of components of bosonic and fermionic degrees of freedom, So, you need to add additional matter fields to this multiplet to balance the number of bosonic and fermionic off-shell degrees of freedom. Okay. So, that you have to do, you have to complete this field representation that you have got from these gauge fields by adding additional matter fields, and you also have to simultaneously modify the transformation rules of the coming from the SU2, 2/n algebra. So, the transformation rules of these gauge fields initially you had obtained by looking at the structure constants of the algebra. So, basically what you need to do is you have to modify these transformation rules, which basically means modifying the structure constants of the SU2, 2/n algebra. So, what you get is also what is referred to as the soft algebra, where the structure constants are field dependent structure constants. Okay. So, in this way you obtain what are called the while multiplet. So, for n equal to 2, for example, apart from the gauge fields that I have written down here, which is listed here in red, you also need to add these fields that I have listed in black, which are the matter fields that are required to balance the bosonic and fermionic off-shell degrees of freedom. Similarly, for n equal to 4, okay, n equal to 4, you do not have any U1 R symmetry, you just have a SU4 R symmetry. So, these are the gauge fields that you have, and then you need to add this whole bunch of matter fields to complete the field representation. So, this together with the gauge field and the matter field, these are called the while multiplet, and you can systematically work out. So, this, yeah, for example, this in n equal to 4, this satisfies this constraint, and this has been worked out by Bakshuk, Deru and Dewitt in this paper. Okay. So, what you get is basically a while multiplet, and so once you obtain the while multiplet, so what you would like to do, as you have asked, what you get from here is conformal supergravity. So, you need to gauge fix some of these symmetries to go from conformal supergravity to Poincare supergravity. So, what you need to do is basically to go from conformal supergravity to Poincare supergravity, you need to add some additional matter fields. You need to couple some additional matter fields to conformal supergravity, because when you gauge fix certain symmetries, then your number of symmetries goes down, right. So, the number of components will go up. Like here, in general, like after adding these extra matter fields, what you get is a 24 plus 24 in n equal to 2, what you will get is a 24 plus 24 while multiplet. Okay. But you know that from when you go from conformal supergravity to Poincare supergravity, you need to gauge fix the spatial conformal transformation, the dilatation, and the SU2 and U1 R symmetry, and the spatial supersymmetry. So, the Poincare, so the basic multiplet of Poincare supergravity will be 40 plus 40 components. So, which is 16 plus 16 more than what you have in conformal supergravity while multiplet. So, if you just work with the while multiplet, you do not get the additional degrees of freedom. So, you need to add 2 extra matter multiplets, which are 8 plus 8 components. So, 2 means it will have 16 plus 16 components, and using these 2 extra matter multiplets, you gauge fix these additional symmetries. So, typically these extra matter multiplets are known as compensating multiplets. So, they compensate for the extra degrees of extra symmetries that you have in conformal supergravity to take you from conformal supergravity to Poincare supergravity. Okay. So, that is the whole program, and one of the important program in this whole thing is to construct invariant actions. So, for example, if you want to construct an invariant action containing the n equal to 2 while multiplet, so typically the way you proceed is you start with n equal to 2 while multiplet, okay, and you take some combination of the gauge invariant objects of n equal to 2 while multiplet in such a way that they transform like a chiral multiplet. So, you know n equal to 2 chiral multiplet, and you know the transformation rules. Okay. So, you take some combination of the gauge invariant objects of n equal to 2 while multiplet, and in such a way that they transform like a n equal to 2 chiral multiplet, or what we say as n equal to 2 reduced chiral multiplet. A reduced chiral multiplet is different from the chiral multiplet in that in the sense that it obeys certain constraints. Okay. A generic chiral multiplet will have some f minus ab, for example, which is unconstrained. For a reduced chiral multiplet, this f minus ab will satisfy some Bianchi identity. And yeah, so there are some constraints that reduced chiral multiplet obeys, and this n equal to 2 wild multiplet, you can actually make it into n equal to 2 reduced chiral multiplet carrying some Lorentz index and SU2 index, okay, where the lowest component of that multiplet will have wild weight 1 and the highest component will have wild weight 2. Okay. So, what you then you basically square this reduced chiral multiplet, and what you obtain is another chiral multiplet whose lowest component will have wild weight 2 and the highest component will have wild weight 4. Okay. Wild weight is basically how it transforms under dilatation, and using that composite multiplet whose lowest component has wild weight 2 and highest component has wild weight 4, you put it into something known as the chiral density formula, which is what I will discuss in the next slide. And after you put it in the chiral density formula, what you have is an invariant action for the n equal to 2 wild multiplet. Okay. So, what is this chiral density formula? So, it basically specifies a quantity in terms of the components of the chiral multiplet that transforms into a total derivative under all superconformal transformations, okay, which is as given in this expression. There are some typos I forgot to fix. There should be a epsilon ij and epsilon kl contracting this ij and kl index, otherwise SU2 indices are not all getting contracted. So, all the SU2 indices should get contracted. So, there is an epsilon ij, epsilon kl that I missed here. Apart from that, this is the chiral density formula, okay. And how one does one so here these things, this C lambda j psi I a b I j and f minus mu nu, okay. These are components of the chiral multiplet, okay, and this psi mu I t I j this same t plus here, and yeah, this t plus, and these are all components of the wild multiplet. So, yeah, basically this action is an invariant action for a chiral multiplet coupled to conformal supergravity, okay. So, this is invariant under all superconformal transformation, invariant under supersymmetry as well as under other superconformal transformation like dilatation, SU2 R symmetry, U1 R symmetry, local Lorentz transformations and so on. Yeah. So, yeah, right. Yeah. So, right, correct. So, how one obtains this chiral density formula? So, if you look at it, a chiral multiplet in flat space, if you know about chiral multiplet in flat space, the highest component of the chiral multiplet transforms to a total derivative. So, basically the invariant action for a chiral multiplet in flat space is just the highest component and nothing else, right, because that transforms to a total derivative. Okay. Now, what you have here is, now you do not have a flat space, you do not have global supersymmetry, you have local supersymmetry. So, so the highest component will not transform to a total derivative, it will transform to a total supercovariant derivative. Okay. So, then it will not be a total derivative under local supersymmetry, but it will be a total supercovariant derivative. And if you expand out the supercovariant derivative, there are a bunch of other gauge fields appearing in there. Okay. So, then you have to systematically add terms proportional to the gravity nodes to such that the whole thing becomes a total derivative under local supersymmetry under other local superconformal transformation. So, that can be systematically approached and done, and this was in fact done using that approach, and one obtained this chiral density formula. Okay. So, which gives us a nice action involving the chiral multiplet coupled to conformal supergravity. C is the auxiliary field, if you want to say. Yeah, C is the highest component, it has the highest wild weight. Yeah. And A is the lowest component. Yeah, A is the lowest component and C is the highest component. And if you look at this action, if you want this, if you look at this this is Lagrangian density. So, so you have to basically take it inside the action with a Weyl-Bein. So, if you see, so when the determinant of E comes here, so the determinant of E has a wild weight minus 4. Okay, so E mu A has wild weight minus 1. So, determinant of E will have 4 E mu A. So, determinant of E will have wild weight minus 4. So, if this whole thing inside the action has to be invariant under dilatation, C needs to have while weight 4. Okay. And psi mu I, similarly psi mu i's have while weight minus half. Okay. So, while weight minus half minus half. So, let us look at this. So, there are 4 gravitinos, minus half into 4 is minus 2. So, this A needs to have while weight 2. Okay. Similarly, you can find out the while weight of other components also. Okay. But this will give us an invariant action under all superconformal transformation, which also includes dilatation, if the chiral multiplet's lowest component has while weight 2 and the highest component has while weight 4. Okay. So, to obtain the action for the while multiplet, what you actually indeed need is this chiral multiplet that you have constructed from the while multiplet, whose lowest component had while weight 2 and highest component had while weight 4. Okay. Okay. So, this is like a master action formula, and if you want to obtain the action for while multiplet coupled to while invariant action containing the while multiplet. So, what you basically do is you construct a chiral multiplet coming from the gauge invariant components of the while multiplet in such a way that the lowest component has while weight 2 and highest component has while weight 4, and you plug it into this formula and you have an action for invariant action for n equal to 2 conformal supergravity. Similarly, if you want to obtain the action for n equal to 2 vector multiplet coupled to conformal supergravity, all that you need to do is write down a chiral multiplet coming from the gauge invariant objects of the vector multiplet, put it into this formula, and you obtain an invariant action for the vector multiplet coupled to conformal supergravity, and so on. But this was like, okay, so there was a systematic way to obtain this formula, but many times this formula may not be sufficient to obtain invariant action for all multiplets. Maybe for if I want to write down an invariant action for a tensor multiplet or some other multiplets, I may not be able to always find a chiral multiplet from the components of that multiplet, or maybe I could still find a chiral multiplet coming from the components of those multiplet, but there might be some other generic action that I miss out if I just rely on the chiral density formula. Okay. So, with that in mind, I ask the following question: is there a generic action principle from which this arises as a special case, this formula arises as a special case, and there could be more generic action that one can write down from that action principle. So, that is what I am going to address. Yes. Yeah.
The way you construct the, let's say the action for n equals to vector.
Yes.
Conformal supergravity, you say we plug in these appropriate values for C, A.
C, A, lambda. Yes. Right. Right. Yes.
Now that would be coupled to some kind of background conformal supergravity.
Correct.
Just
Yeah. Exactly. So, these are the components of background conformal supergravity. Psi mu I, T I j, and these things are background supergravity. Yeah.
Pure conformal supergravity, all we have to do is take the W square.
W square.
And then substitute.
Yeah. Yeah. Right. Right.
So, to have a dynamical conformal supergravity plus vector,
Yeah.
you just have to add those two.
Add those to action. Right. Yeah. So, typically for in going from n equal to 2 conformal supergravity to n equal to 2 Poincare supergravity, you need the while multiplet, and as I said, you need 2 compensating vector multiplet. One of the compensating vector multiplet is the vector multiplet. The other compensating vector multiplet could be either a tensor multiplet or a hyper multiplet or a nonlinear multiplet. These are different kinds of multiplet that you could use as a compensator. Okay. So, if you want to write down an action, so basically then what you need is not only action for n equal to 2 while multiplet and vector multiplet, but also you need to know the action for n equal to 2 hyper, tensor or nonlinear multiplet. Okay. So, for tensor multiplet, for an action containing tensor multiplet, this chiral density formula may not be useful. Okay. So, with that in mind, we try to understand some generic action principle from which this chiral density formula just arises as a special case. Yeah.
The gauge fields for dilatino and the R symmetries don't appear in this.
Gauge symmetries for dilatino?
Gauge fields. Suppose we turn on background value for P, B and A.
Yeah.
They don't couple to a chiral multiplet.
Oh, you are saying gauge fields for the dilaton. Okay, so right. Yeah, for the dilatation and the R symmetry, they don't couple, they don't come here. Yeah, they don't come here. So, what you have is basically We will see when we will understand this when we look at the generic action principle that we write down. So, the bare gauge fields that are that can appear in your action are the Vellbine and the Gravitino, and other gauge fields are all hidden inside your supercovariant objects. Like for example, here it is here you have a supercovariant field strength. So, that supercovariant field strength contains some gauge fields.
So it's the ordinary field strength plus
right, plus supercovariantizations. Yeah. So, the bare gauge fields that come are only the Vellbine and the Gravitino. Yeah. Okay. So yeah. So, let me come to this superform action principle. Okay. So, I will start from some very basic things that we all know. So, let us consider a larger manifold capital M, which is whose dimension is D, and inside that larger manifold I have a closed smaller manifold N of dimension small d, and I integrated D form J on that smaller submanifold and sorry, what happened? Yeah. So, under arbitrary diffeomorphism on this M, J transforms like this. So, this is a diffeomorphism of J, where I xi is the interior product, and we know that a diffeomorphism of any form takes this particular form. And so, if you demand that this action is invariant under all diffeomorphism, not just diffeomorphism confined to the smaller submanifold, but under all diffeomorphism, then all that you need to impose is dj is equal to 0. This goes to 0 because you have considered a closed submanifold, and so all that you need to impose is dj is equal to 0. So, if j is closed, then this action is invariant under all diffeomorphism in M, okay, and not just diffeomorphism on on the smaller submanifold N. Okay. So, this is very well known and we all know this. So, what we would like to do is we would like to use this idea where where this N is the full space time manifold, and capital M, which is a larger manifold, is something where we have geometrized some gauge symmetries. Okay. So, for this let us consider this simple bosonic example, which is the T equal to 3 gauge Chern-Simons term. Okay. So, this so here I have considered a non-abelian gauge field and this Chern-Simons term, which we know that if we take if we integrate this on the 3-dimensional space-time manifold, it is gauge invariant. Okay. To see that in the language of the previous slide, okay, let us look at the gauge transformation of this AI. We know that the gauge transformation of AI is it takes this form where this f k j I are the structure constants of the non-abelian Lie algebra. And so, now what we do is we promote this AI, the gauge field, to a super Vellbine, okay, where we have geometrized this gauge symmetries, and we are considering a higher dimensional manifold where AI is a part of the Vellbine. Okay. Small E A are the Vellbine on the space time manifold, and AI are the Vellbine in the other directions. So, we have geometrized that direction, and yeah. So, what we do is we define a generalized interior product for the Vellbine. So, for the super Vellbine, the generalized interior products is that it takes this form where xi, where this xi A is basically the contraction of xi M, where xi M is the diffeomorphism in the full larger manifold, of which small m is in the smaller manifold, and the other direction is basically the gauge symmetry. Okay. So, in that sense, if you define the interior product of this Vellbine, it is just xi A, which has only diffeomorphism in the smaller submanifold, and for the gauge field, you have the usual interior product that you have for diffeomorphism on the submanifold, but you also have the gauge parameter. Okay. So, these are the interior products of the Vellbine and the gauge field. Okay. So with that and the definition of the field strength. So the field strength is defined like this. So using this definition of the field strength, I can write down the exterior derivative of AI in this way, okay, where I interpret this as in the following way. It's a two form. Now this two form has legs along the Veblen on the smaller manifold n, and also legs along the Veblen in the larger manifold n. So these are expanded in terms of the super Veblen's. So now I interpret these as super Veblen's. These are the Veblen's along the smaller submanifold n, and these are the super Veblen's. These are the gauge fields which are now promoted as part of the super Veblen. Okay. So you can easily check that once you have this DAI and you know what are the interior products of these Veblen's from the previous slide which I had given earlier. So these are the interior products of EA and the interior products of AI. Okay. So if you just put the interior product, so you know, then you can calculate what is IISER interior product of DAI, because you know interior product of is an interior product of A. Okay. And if you if you restrict yourself to the interior product along the gauge transformation parameter, you can easily show that the gauge transformation of this AI is nothing but this, where this interior product is along the gauge transformation direction. So yeah, so this IISER AI had a diffeomorphism and a gauge transformation. So if you just take the gauge transformation part, you will obtain the gauge transformation of AI. Okay. If you take the diffeomorphism part, you will obtain the diffeomorphism of AI. Okay. Okay. So what we have basically shown here is that the gauge transformation of AI is nothing but diffeomorphism along the normal direction orthogonal to the space-time manifold. Okay. So now we geometrize the gauge symmetries. So you have a smaller submanifold, and then you have some additional directions where you have geometrized the gauge symmetry, and the gauge symmetry is gauge transformation of AI is nothing but diffeomorphism along that direction. Okay. This is something we also already know.
Is also Kaluza-Klein setup?
It's not a Kaluza-Klein setup. So we are not doing any. It's similar to that. It's not.
Mathematically, does it end up being that?
Yeah, yeah. It's similar to that, but we are not doing any Kaluza-Klein reduction or something. We are basically taking the geometrize the symmetries, and our action is along a space-time manifold, which is defined at a particular slice of this larger geometry. Yeah.
But essentially, these expressions would be that of the.
Yes. Yes.
If you have some graviton
Yeah.
associated with vibration of some sphere
Right.
or something,
Yeah. Yeah.
then they would obey these types of.
Right. Yeah. Right.
And what is your super form in this case?
Okay. So that is the super form that I had written. This is the super form. This is the super form.
No, but I thought super form you want to write it as some generalized, as a function of some generalized
Yeah.
real line.
Correct. So if I expand this, if I use this dA, so this is my dA. Okay. If I put it in this dA here, okay, so I'll basically have a three form, okay, with two legs along the actual Veblen and one leg along the gauge field, and three legs along the gauge field. Okay, so these are my super Veblen. So small ea and capital AI are my super Veblen. Now this super form is expanded in terms of the number of factors of this super Veblen, what kind of super Veblen it is carrying. Okay, so dA had two small e's and two capital A's. Okay, so if you put that here, okay, so you have a term in the super form which are two small e's and one capital A. It's a three form. So it's okay. So that three form has expansion into two small e's and one capital A and three capital A's. Okay, and to show that this is gauge invariant, so you need to know that the gauge transformation of the super form also I can write it as an exterior derivative of the interior product of J and the interior product of the exterior derivative of J. Okay. So this gauge transformation is also, gauge transformation of J is also diffeomorphism along the additional direction. So the gauge invariance of J basically boils down to solving dj is equal to 0. So if I want to check that J integral of J over the space time manifold is gauge invariant, I only need to show that dj is equal to 0. Okay. So now what dj turns out to be, if you use whatever j I had given you and you calculate dj, it turns out to be trace f wedge f. Now j, if it was a 3 form in the if it was a 3 form confined to the smaller submanifold n, it's a top form in n. So dj will be identically 0. But in this case, I am not considering j as a 3 form in n. I am considering j as a 3 form in the larger manifold M. So dj won't be identically 0. Okay. So because it is not a top form in the larger manifold M. But dj, the calculation of dj turns out that it is trace f wedge f, and f has only legs along the whalebine. So f is basically fab ea wedge eb. Okay. So trace f wedge f is basically something, this is the some fab fcd trace, and ea wedge eb wedge ec wedge ed. Now this is a 4 form where this a b c d index takes over 3 values. Okay. So that becomes 0. Okay. So that was, I mean, that is why that relative factor between a wedge dA and a wedge A matters, so that when you calculate dj, you only get f wedge f. You don't get anything which has bare a, I or aj. Okay. So that makes this 0. So this is 0 not because it's a 4 form in a 3-dimensional manifold. This is 0 because it's a 4 form containing this a b c d index which runs over only 3 values. So that is why it is 0, and that is the reason j is gauge invariant.
What is the interpretation of that extra term with 1a and 2 usual terms A has the
Huh.
term with 2 a's and the term with 3 a's.
Yeah, but this is a usual Chern-Simons free form, right?
Where a is just the usual gauge field.
Where a is usual gauge field, but dA is not the usual gauge. I mean, if you take d of a, that has 2 whalebine and 2 a's, right? So when you expand this out in terms of the number of factors of whalebines and a's they carry, you have one term which has 2 whalebine and 1 a, and you have one term which has 3 a's. Okay. So this is the bosonic example. I mean, wanted to give you is that so basically, if you geometrize a gauge symmetry, to a larger manifold, so invariant under that gauge symmetry basically amounts to saying that the super form that you are using in your action has to be closed. Okay. So that is the takeaway from this discussion. So now we turn to the supersymmetry case, okay, where we geometrize the ordinary supersymmetry. So by ordinary supersymmetry, I mean that in conformal supergravity we had 2 kinds of supersymmetries. So I geometrize the ordinary supersymmetry by putting the gravitino as a part of the whalebine. Okay, just like what we did there for the gauge field, here I put the gravitino as a part of the whalebine. Okay, so the manifold in this, this is manifold. The manifold in this case is nothing but the superspace. So this is the super whalebine, which has legs along the normal space-time direction, and this is the superspace directions. And the whalebine along the normal space-time direction can be decomposed into the whalebine and the gravitino, where this alpha underline index is a combination of your spinor index as well as any other index that it can carry, like the SU2 index or any other R symmetry index, right. So for example, in n equal to 2 we had psi mu I, so it had a spinor index and an SU2 R symmetry index. Okay. So this alpha underline together takes care of that. Okay. So we'd be interested in supersymmetric actions in 4 space-time dimensions, where integrate a 4 form over the space-time manifold. Okay. So we'd like to integrate a 4 form like this over the space-time manifold. Okay. So this EA, EB, EC, ED, etc., these had legs along the space-time direction as well as the superspace direction. Okay. So when you integrate it over the space-time manifold, so only those terms come yeah, which has legs along the space-time direction. Okay. So, yeah, so if you integrate it over the space-time manifold, this is what you get, and this. So what I am doing is I have suppressed the wedge product symbols. Okay, so maybe I should tell that. So now whenever I write 4 forms, the wedge products are assumed. It is there. I have just not written it down. Okay. So similarly, there are also wedge products here, and I can write these wedge products over these 1 forms as epsilon mn pq times d4x. Okay, so there is a x missing here. There is a d4x. Okay, that's the integration measure. Okay. So this is some block. I will call it as a block. Okay, it's basically covariant, and these are the super Villebines, which is either a Villebine, EMA, or the gravitino. Okay, so your action will boil down to writing. I mean, arranging it in such a way that it carries total 4 numbers of Villebines and gravitino. So it could be either all 4 are Villebines, okay, or some are Villebine, some are gravitino. You could have all 4 gravitino. You could have 3 gravitino, 1 Villebine. You would have 2 gravitino, 2 Villebine, 1 gravitino, 3 Villebine, and 4 Villebine. Okay, so so that is how we will arrange these actions. Okay, and so what we have done is we have only geometrized. So this, I mean, the supergravity theory has many gauge symmetries. It has dilatation, it has local Lorentz transformation, it has SU2 R symmetry, U1 R symmetry, spatial conformal transformation, S supersymmetry, and Q supersymmetry, out of which we have only geometrized the Q supersymmetry. So because it is easier to handle the other symmetries. Okay, so it's easier to handle the other symmetries. So this 4 from J is assumed to be invariant under every other gauge transformation, where this M is local Lorentz, this is dilatation, this is SU2 R symmetry, this is U1 R symmetry, spatial conformal transformation, and this is S supersymmetry. Okay, and this can be ensured by taking each of these blocks that I have here. Okay, I take each of these J, D, C, B, A as invariant under spatial conformal transformation. Okay, and it has the required while weight or chiral weight. By required while weight or chiral weight, I mean that suppose you look at a term when all 4 are gravitinos. Okay, so gravitino has a while weight of -12. Okay, okay. So this block, so when all 4 are gravitinos, then this 4 gravitinos will have while weight -2. Okay, so this block will need to have while weight 2. Okay, and if all 4 of them are left-handed gravitinos, okay, it will have a chiral weight. By chiral weight, I mean how it transforms under the E1 R symmetry. Okay, so the left-handed gravitinos have chiral weight of -12. Okay, so if all 4 of them are left-handed gravitinos, then it will have chiral weight of -2. So this block will need to have a chiral weight of +2, so that this whole term is invariant under dilatation and E1 R symmetry. Okay. Similarly, depending on what kind of SU2 indices these gravitinos are carrying, like whether there is all the 4 SU2 indices are contracted with some epsilon ij or delta ij, or there is some SU2 index that is left over. Depending on that, this block also may need to carry some SU2 index, which means it will transform in some way under the SU2 transformation, or it could be invariant under SU2 transformation. Okay, and and local Lorentz transformation also, by looking at the local Lorentz transformation of these 4 forms, you can also deduce what kind of local Lorentz transformation this block will have. Okay, that is easy to implement. Under S transformation, so what will happen is that these blocks will need to transform into each other, because under S transformation, your gravitino goes to a Villebine. Okay, gravitino transforms to a Villebine under S transformation. Okay, so if you take a 4 gravitino block here, under S transformation, it will go to a block which has 3 gravitino and 1 Villebine. Okay, so the 4 gravitino block and the block that comes with 3 gravitino and 1 Villebine have to be related to each other by S transformation. Okay. Okay, so that is also easier to implement because the Vierbein is S invariant and gravity simply goes to Vierbein under S transformation. So, that is also easier to implement. So, we will implement it in such a way that this 4 form J is assumed to be invariant under all these bosonic transformation as well as S supersymmetry. Okay. And the only thing that we have geometrized here is the Q supersymmetry, and invariance under Q supersymmetry is ensured by demanding that this 4 form J is closed in the extended space, which is a superspace. Okay. So, demanding that J is closed under is basically also similar to demanding covariant closure, because we have already assumed that J is invariant under these transformations, and this covariant closure is this nabla is covariant with respect to all this transformation that we have already assumed that it is invariant. Okay. Okay. So, the nabla is nothing but covariantization under these transformations: local Lorentz, dilatation, U1 R symmetry, SU2 R symmetry, special conformal, and S supersymmetry. Since we have assumed that we have by construction J is invariant under this transformation, so the closure is the same as covariant closure. Okay. Okay. Covariant closure is easy to implement, that is why we use this covariant closure. Okay. Okay. So, basically you need to write down this 4 form and demand that it is covariantly closed. Okay. You by construction you make it invariant under all this bosonic transformation as well as S supersymmetry, and you demand that it is covariantly closed, which automatically makes it invariant under Q supersymmetry also. Okay. That is how we will construct these invariant actions. Okay. Okay. So, let us try to implement this in obtaining n equal to 2 chiral density formula that I had shown you earlier from the superform action principle. Okay. So, in order to do that, so let us note how covariant exterior derivative acts on various objects. Okay. So, your 4 forms, as I told you, you can write it as many terms, and each of these will contain some factors of Vierbein, some factors of Gravitino, and some covariant objects. Right. So, you had this EA, EB, EC, ED, J, DC, BA, and this EA, EB, EC, ED could be either a small EA or a psi mu I, psi mu alpha, and this J, DC, BA is a covariant object. Okay. So, we need to know how this covariant exterior derivative is acting on each of these terms. Okay. So, first we need to know how the covariant exterior derivative acts on the Vierbein. Okay. So, it acts on, so it is a 2 form, Vierbein is a 1 form. Okay. So, the covariant exterior derivative is a 2 form, and that is given as is. Okay. Okay. So, this is a wedge product of this with this. Okay. I have written it in a 4 component notation. Okay. So, these are my 4 component spinors. Okay. So, this is a 2 form and this is given as this. Yeah. So, that is what I am saying, that so the origin of this is coming from the curvature constraint. Okay. So, we have imposed this curvature constraint, which is RP mu A is equal to 0. Okay. So, from there we see that the covariant exterior derivative on E is nothing but this. Okay. So, that is coming from the curvature constraint. Okay. So, that is how covariant exterior derivative is acting on E. Okay. Similarly, it acts on the Gravitino in this fashion. So, this is my left-handed Gravitino. So, its gamma 5 eigenvalue is plus 1, and this is my right-handed Gravitino, its gamma 5 eigenvalue is minus 1. Okay. It acts on this so I will define this. Okay. So, I am defining various things here. So, I am defining something called T0, which acts only on EA. Okay. By definition, T0 on EA is this. Okay. Similarly, my covariant exterior derivative on psi I am writing it as T3 by 2 psi I plus T1 psi I will define this, and for psi lower I write it as T bar 3 by 2 psi I plus T bar 1 psi I, okay, which is defined as this. So, T3 by 2 psi I is basically wedge products of 2 Vierbeins contracted with a curvature tensor of R for Q supersymmetry, curvature for Q supersymmetry. Okay. So, I call it T 3/2 because the curvature RQBA has a while width 3/2. Okay. Right. So, this notation I am following is basically the while width of the super covariant thing that is appearing on the right hand side. Okay. So, for EA there was no super covariant thing that was appearing here. So, that is why I called it T0. Okay. So, T 3/2 psi I is given as this, T1 psi I is given as this. So, it is a wedge product of a Vierbein with a gravitino, and there is a gamma dot Tij. So, Tij was, if you remember, we had a T minus AB Ij in the while multiplet. Okay. So, gamma dot TAB Ij is nothing but gamma AB T minus AB Ij. Okay. So, there is a gamma AB contracted with TAB Ij. Okay. So, that is how T1 acts on psi I, and similarly T bar is the Hermitian conjugate of this is, and this comes so this this basically comes from the definition of the curvature of ordinary supersymmetry. Okay. So, as I told you earlier that if when you start from the super conformal algebra, you know the structure constants. Okay. Once you have modified everything, all the transformation and all, you know the structure constants. So, from the structure constants you can write down the curvatures, standard non-abelian gauge theory, right. So, once you write down the curvature, okay, so this is the curvature. Okay. So, from this curvature you can read off what is the exterior covariant exterior derivative on psi I. Okay. So, that is what we did in the Chern-Simons example also. Okay. From the curvature from F mu nu, we wrote down what is d of AI, right. So, that is the same thing that we are doing here. From the curvature we are writing down what is the covariant exterior derivative on gravitino. Okay. Okay. So, covariant exterior derivative on gravitino has two Vierbein and one Vierbein and one gravitino. Okay. So our this superform J had components like there was Vierbein, there was gravitino, and there were super covariant objects. Okay. So, we saw how the covariant exterior derivative acts on the Vierbein, we saw how the covariant exterior derivative acts on the gravitino. Okay. So, now let us see how the covariant exterior derivative acts on the super covariant objects. So, this phi is any super covariant objects, it can carry any indices or anything, but it is super covariant. Okay. So, the way we write it is like this, where these are defined here. Okay. So, this dA phi is the fully super covariant derivative of phi. Okay. Fully, it is super covariant under all transformation including Q supersymmetry. Okay. So, how we wrote this down? Okay. So, del phi. Okay. So, del phi to begin with. So, this was covariant with respect to all other gauge transformation except Q supersymmetry, right. That is how we defined our del phi. Okay. So, this is basically equal to EA del A phi. Okay. So, where this derivative is covariant to all gauge transformations except ordinary supersymmetry. Okay. So, now what we have done is we have added and subtracted Q covariantization. Okay. Okay. So, what we have done is we have made this into EA dA phi. Okay. So, dA phi is nothing but del A phi plus yes. So, dm phi is basically del m phi minus half delta q psi m phi. Okay. So, it's basically it is the usual usual covariant derivative which is not covariant with respect to supersymmetry transformation. You covariantize that with respect to supersymmetry transformation by subtracting the Q supersymmetry of that object where the supersymmetry transformation parameter is replaced by half the half times gravity. That is how you supercovariantize your supercovariant derivative, right. So, you basically have taken this minus of this into this, minus of this to this by into this by making it a supercovariant derivative. So, plus what is remaining is basically plus half psi bar k q k phi plus half psi bar k q k phi. Okay, q k is the generator of supersymmetry transformation. So, this two terms is nothing but delta q with the parameter replaced by half psi k acting on phi. Okay. Okay. So, you have added this and subtracted the same thing and made this into a supercovariant derivative. The reason is we want to organize our calculations into factors of Weyl-Bein, gravitino and supercovariant objects. Okay. So, that is the reason why we transform this into supercovariant objects. So, dA phi is a supercovariant object, supersymmetry transformation of phi is also another supercovariant object, right. Okay. So, now this del phi has one factor of Weyl-Bein coming from here, one factor of gravitino coming from here and one factor of right handed gravitino coming from here. Okay. So, now after having all these ingredients we can, okay, so now your to summarize this covariant exterior derivative is a sum of all these things, where all these things depend will be turned on depending on what fields they are acting. So, if del is acting on the Weyl-Bein, you only have T0 acting on that, other things do not play a role. If del is acting on gravitino, you have either T1 or T3 by 2 or T bar 1 or T bar 3 by 2 depending on whether it is a left handed or right handed gravitino. Okay. If it is acting on a covariant object, you only have these things contributing. Okay. So, that is how we will organize our calculations. Yeah. So, let us use all of this above information to derive. Okay. I will not derive the chiral density formula, but I will derive a few layers of that, one layer of that, which will basically tell you how to proceed. Okay. So, to do that you have to start with an ansatz. You have to start with an ansatz for a term containing the maximum number of gravitino. Okay. So, as we saw that the maximum number of gravitino that we can have is 4, okay, EA, EB, EC, ED. Okay. So, when all 4 of them are gravitino, okay, you propose some term like that, and starting from there you can construct your entire invariant action. Okay. So, that proposal is like this. So, for chiral density formula what you see is that if you propose your highest gravitino block of this 4 from J in this way. So, this is containing 4 right handed gravitino and the Hermitian conjugate of that contains all 4 left handed gravitinos, okay, and you do it like this. Okay. So, all the 4 right handed gravitinos have some SU2 index and you contract them with the invariant tensors epsilon ij and epsilon kl, and this block therefore is a scalar, it is a SU2 scalar. Okay. It is a SU2 scalar, it is scalar under Lorentz transformation also. Okay. It has Weyl weight 2 because as I said these are minus half Weyl weight. So, this needs to have Weyl weight 2 and these are right handed gravitinos. So, these are plus half chiral weight. So, this needs to have chiral weight minus 2 and this will have chiral weight plus 2 because these are coming with left handed gravitinos. Okay. Yeah. So, now the thing is yeah. So, we will start with, so we know, so as I said we know what are the properties of this object of this composite under Weyl transformation, chiral transformation, SU2 transformation, Lorentz transformation, and we also know that this has to be S invariant. Okay. This has to be S invariant because under S transformation, okay, under S transformation the psi goes to a Weyl-Bein. Okay. The psi goes to a Weyl-Bein. Right. Wait. Yeah, psi goes to a Weyl-Bein. So, under S transformation, this you will get this block going to another block with one Vlbine and 3 gravity nodes. Okay, one Vlbine and 3 gravity nodes. Okay, so, sorry, I didn't mean that. Okay, sorry. So this I wanted to find the S transformation of A. So if you take S transformation of A, so that has 4 gravity nodes, 4 gravity nodes. Okay, but the other blocks, so this is the block with highest number of gravity node. The other block will have lesser gravity node and one Vlbine. Okay, so other block will have lesser gravity node and one Vlbine. So from the S transformation of that, I cannot get something which has 4 gravity nodes, because Vlbine is S invariant and gravity node goes to Vlbine under S transformation. Okay, so which means that if I have a J E psi bar cube, okay, if I take the delta S of that, I am at most going to get E square psi bar square, right? Okay, because psi bar will go to E. Okay, E square psi bar square. I am not going to get a psi bar 4 or a psi 4. Okay, so this has to be S invariant. Okay. However, the S transformation of this composite, the block of this composite will be related to A. As I said, so this J E psi cube has a covariant object. Okay, so if I take the S transformation acting on that covariant object, that has one Vlbine and 3 gravity nodes. Okay, and here also I can get one Vlbine and 3 gravity node when the S transformation is taken on this gravity node. So the S transformation of that composite will be related to this A. Okay, so the S transformation of the next composite, which has one Vlbine and 3 gravity node, will be related to A. Okay, but A has to be S invariant. Okay, so the composite with maximum number of gravity node has to be S invariant. Okay, but so now we need to see, we need to demand the covariant closure of J for it to be invariant under Q supersymmetry. Okay, so for that we need to decompose our calculations of this covariant closure of A into the number of factors of Vlbine and gravity nodes that it carry. Okay, so del of J is a 5 form, J is a 4 form, so del of J is a 5 form. Okay, so we first start with del of J, which contains 5 right-handed gravity nodes. Okay, it's a 5 form. Okay, so the number of Vlbines and gravity nodes should add up to 5. Okay, so we start with a simple thing, that del of J contains 5 gravity nodes and all 5 of them are right-handed. Okay, so that is only going to come from when I take delta bar half on A, because delta bar half on a covariant object has a right-handed gravity node. Okay, and no other thing, because if either T1 or T3/2 acts on this gravity node. Okay, so if T1 acts on this gravity node, you get one Vlbine and one left-handed gravity node, right? If T bar 3/2 acts on this gravity node, you get 2 Vlbines. Okay, but I'm interested in del of J, which has 5 right-handed gravity nodes. So that will only come if delta bar half acts on this. Okay, so delta bar half acting on that is this, and this thing has to be 0, because this is the only place it is coming from. So this has to be 0, means that A has to be invariant under right supersymmetry. Okay. Okay, so this A has to be okay, and that's the property of chiral multiplet we have already seen. Okay, chiral multiplet means that the lowest component is invariant under one of the supersymmetry transformation, either left or right, depending on whether it is a chiral multiplet or an anti-chiral multiplet. Okay, so this was simple. Now let us look at terms in delta J containing 4 right-handed and 1 left-handed gravity node. Okay, so that will come from delta half of the block that I had already written down, but that will also come from T0 of another block which has 1 Vlbine and 3 right-handed gravity node. Because Vlbine, when T0 acts on Vlbine, if you remember, it goes to 1 left-handed and 1 right-handed gravity node. Okay. T0, when it acts on the Vlbine, it has 1 left-handed and 1 right-handed gravity node, one upper I and one lower I. Okay. So if you are interested in delta j, which has 4 right-handed and 1 left-handed gravity no, that is going to come from this, which we already know, which we have already proposed as an answers, and from T0 of another block which contains 1 Weyl-Bine and 3 right-handed gravity no. Okay. So, let us evaluate the thing that we already know. So, we know j psi bar 4, okay, and we need to find out delta half on j psi bar 4. Okay. So, that will be simply so if you look at this is j psi bar 4. So, delta half will act on A, okay, that is basically psi bar upper m, q lower m on A, okay, and that q lower m on A is what I have defined as rho m. Okay. Huh. Which one? Previous slide. Yeah. Huh. One before this. Yeah. These are oh okay, sorry. So when I say psi bar to the power 4, it has these are all right-handed gravity nodes, and I am writing it in a 4-component notation. Okay. So these are these are all right-handed gravity nodes, but Lorentz invariant combinations of that. Okay. So this is a bilinear psi bar I psi j, and this is a bilinear psi bar k psi l. Okay, wedge products of that, because gravity node is one form. Okay, but I have written it in a 4-component notation. Okay. Yeah. So when I when I take delta half of that, this becomes this, and now if coming from here to here, what I have basically done is I have used an identity where if I antisymmetrize this epsilon ij with psi m, that is 0, in order to bring this ij index into this gravity. Okay, because we are in SU2, so if you antisymmetrize 3 index, it will be 0. Okay, that's standard trick that we always use. So you antisymmetrize m and ij and set it equal to 0, which will basically relate this to this, where this ij index has come on this gravitino, and this m index has gone to the Levi-Civita. Okay. So once I have this ij index here, I can use the Fierging here to write it as a torsion term Ta, where Ta was defined as minus half psi bar j. Okay, it was defined as minus half psi bar j gamma a psi j. Okay. So once you do the Fierging here, you will extract Ta, and so I have done some Fierging here. So you have a psi bar k gamma a rho l. Okay, I have done some rearrangement of index, renaming of indices, and so on. Okay, but it's a standard exercise to do this, and what you observe is that delta half of this is not 0. It goes to something, but that something can be cancelled by proposing. So rho m is qma, as I said. That something that I get from delta half of this can be cancelled by proposing a j e psi bar cube, where I basically replace this by a Ea, so that because when T0 acts on Ea, it gives me a Ta, right. So if I replace this by Ea and and this by plus, and just replace this by Ea and add it to my j, so when T0 acts on that, it will cancel with this. Okay. So if I just propose this j e psi bar cube as this. Okay. Okay. So when I take T0 of that, okay, so I'll get a minus 1 by 4. I think this should have been a minus 1 by 4 here. Okay, because my exterior derivative I am taking from this side. Okay, so it has to jump 3 forms, so I'll get a minus sign because of that. Okay, so T0 of that will be a minus 1 by 4 Ea. So if it is a minus 1 by 4 Ea, that will be plus 1 by 4 Ta, and that will cancel with this minus 1 by 4. Okay, so I need a minus 1 by 4. This is the typo. This is a minus 1 by 4 Ea. Yeah. Okay.
How much do you take?
15 minutes. Yeah. Yeah. So this by adding this term to your 4 form, you basically cancel this one, and so delta of j containing 1 left-handed gravitino and 4 right-handed gravitino goes to 0 by adding this. And that's exactly what comes in your chiral density formula. If you so this is basically this, yeah. So if you see, this is okay, this with this, that is A, and this with this, where this psi L was my rho L. Okay, and chiral multiplet transformation rules also tells you that under right supersymmetry transformation, A goes to psi L. Okay, and that's what we exactly got here. So we not only obtained the density formula, we also obtained the supersymmetry transformation. Okay, so supersymmetry transformation of A, it is invariant under right supersymmetry transformation because QM of A was 0, and the left supersymmetry transformation appears in the composite in the next block. Okay, so A appears in the psi to the power 4 block, and rho appears in the E psi cube block. Okay. Okay, so in this way we obtain. Okay, so using this formalism, we start from an answers. Okay, and we obtain a density formula together with the supersymmetry transformation law of the multiplet that appears in this density formula. So I didn't assume that it has to be chiral multiplet or anything. I just started with the answers for the 4 gravity no term, and I obtained this density formula together with the transformation rule. Okay, and you continue if you proceed this way. Okay, so I have just shown one layer of computation. Okay, you have to do this for more layers. You have to look at delta of J, which has 2 Vlbine and 3 right-handed gravity no, or 2 Vlbine, 2 right-handed gravity no, and 1 left-handed gravity no, and so on. Okay, so you have to do all these computations. Okay, and you have to demand covariant closure of J at each layer. Okay, and you will obtain the supersymmetry transformation law of the composites that appear in the density formula together with the density formula. Okay, so it's a kind of unified framework which gives you the density formula as well as the supersymmetry transformation of the multiplet that comes into the density formula. Okay. So this is I mean one way, I mean this is a new way of looking at the chiral density formula, but our purpose was to obtain a new density formula which cannot be captured by the chiral density formula. You can show that if you are interested in a density formula which starts with 4 gravity no term in n equal to 2 supergravity, then the chiral density formula is the most general formula. So if your starting point is 4 gravity no, okay, that one can show. I mean, you need to argue a little bit, but one can show that is the most general density formula which has 4 gravity no as the highest number of gravity no in the action. Okay, but one can pick the starting point itself to obtain a different density comprising of components of a different multiplet, which is not a chiral multiplet, and that's what we do here. Okay, we modify the answers. We say that our starting point is not a 4 form whose maximum number of gravity no is 4 gravity no, but we start with the starting point where the maximum number of gravity no is 3 gravity no. Okay, so our starting point is a is a fermionic. So the block that comes here is a fermionic block. Okay, so the lowest component of this multiplet is a fermion. Instead of being a boson, it's a fermion. Okay, so the chiral density formula was based on a multiplet whose lowest component was a boson. Okay, that's because that arises in a 4 gravity no block. Okay, so here it comes with a 3 gravity no block. So the lowest, this is my lowest component of this multiplet, which will make up my density formula, and that is a fermion. Okay. Okay, so this is my answers. This is just the Hermitian conjugate of this. Okay, so here I have 2 right-handed gravity no and 1 left-handed gravity no, and the Hermitian conjugate is opposite. I have 2 left-handed gravity no and 1 right-handed gravity no, and this block sigma ijk that I have defined here is completely symmetric in its SU2 index, which means that it belongs to the irrep 4 of SU2. Okay. So one thing that one has to show here is that if you take delta j of this, if you take the covariant exterior derivative on this. So there will be a term where T0 acts on this Wehlbein. Okay. So when T0 acts on this Wehlbein, you will get one left-handed and one right-handed gravitino. Okay. So from this term, when T0 acts on this, you will get one left-handed and one right-handed gravitino, and you already had two right-handed and one left-handed gravitino. So delta J of that will contain basically 3 right-handed and 2 left-handed gravitino, and that has to vanish on its own, because there is no other term that it could come from. It could have come from another higher order term which had higher number of gravitinos, but that is not present in my answers. My answer starts from a term which has which has one Wehlbein and 3 gravitinos. 2 of them are right-handed and 1 of them left-handed. So that has to cancel on its own. And indeed, what I am going to show is that that is actually identically cancelling. So you have to do a little bit of algebra. So this is T0 of EA. Okay, so this is T0 of EA, what I have written down here. Okay, so what you basically need to do is you need to do some Feerging. Okay, so when you do Feerging, you arrive at this. Okay, and you after you arrive at this, you realize that psi bar I psi L, it is antisymmetric in I and L. Okay, because it's a wedge product. I mean, usually psi bar phi is equal to phi bar psi, but here it's also a wedge product. So there is therefore another negative sign because of that. So this is antisymmetric in I and L. This is antisymmetric in L and J. And since you are in SU2, anything antisymmetric in I and L is proportional to epsilon IL, right? So this is proportional to epsilon IL. This is proportional to epsilon LJ. So epsilon IL, epsilon LJ is delta IJ. Okay, so delta IJ means this becomes IM, and this is symmetric in I and N, and this is antisymmetric in I and N. Okay, so that becomes 0. Okay, so that's very easy to show. So that that's a basic. I mean that's a check that our answer is right. That the delta of J with the highest number of gravitinos goes to 0. Okay, the highest number of gravitino in delta of J is 5. Okay, and that goes to 0 on its own. Okay. So now what you need to do is, okay, so I'll just show a few layers of computation, like starting from that starting point. Okay, you can obtain the next block in this multiplet that will be related to the supersymmetry transmission of the sigma ijk, and that block how it appears in the density formula. Okay, that is the whole purpose of this program. Okay, you start from a lowest component of a multiplet. Okay, and using this formalism, you obtain the supersymmetry transmission of that block, and the terms appearing in the supersymmetry transmission of that block appears in the density formula. Okay, so that is how we will see. Okay, so now we'll look at in delta J, we will look at term containing 1 Wehlbein, 3 right-handed gravitino, and 1 left-handed gravitino. Okay, so that comes from delta bar half of something that we already know, and T0 of something that we don't know but we can find out. Okay. So yeah, so to calculate delta bar half of things that I know, I define something. Okay, I define how the supersymmetry generator acts on this sigma ijk. Okay, so in this way of defining things, basically means that I have defined the right supersymmetry transmission of sigma ijk. So right supersymmetry transmission of sigma ijk basically goes to this. Okay, where these blocks AAB, IJKL, BAB, IJ, AIJKL, and BIJ are defined here. Okay. Okay. So these are all totally symmetric in its indices. Okay, that's how my SU2 representations are anyway defined. Okay, these are objects which are totally symmetric in their SU2 indices. Okay, so AIJKL is totally symmetric in all its SU2 indices, and therefore it belongs to a 5 representation of 5 irrep of SU2. This belongs to a 3 irrep of SU2. This also belongs to a 5 irrep of SU2, and it is antisymmetric in the Lorentz index and self-dual. It is antisymmetric and self-dual in the Lorentz index, because gamma AB is self-dual, because that is coming with the right spinner, right chiral spinner. So it's self-dual. And similarly, this is also totally symmetric in its IJ, so it belongs to irrep 3 of SU2, and it is totally antisymmetric in the Lorentz indices and self-dual. Okay. So, using these blocks that appear in the right supersymmetry transformation of sigma ijk, your delta bar half of the composite that I had written down can be written in this way, okay, where this BKL, A, B, JMNP and BCDKL are defined as blocks that appear in the right supersymmetry transformation of sigma ijk. Okay. So, you can do that, I mean that is simple exercise, and if you see that the first and third term here, the first and third term can be cancelled by proposing a J E square psi square. Why? Because you have a EA TB here, and that is contracted with a gamma AB here, which is antisymmetric in A and B, and that is required. If I want to if I want to cancel this by proposing a J E square psi square, that will contain a EA EB, which has to be antisymmetric in A and B, right. So, therefore, this also needs to be antisymmetric in A and B. Okay. So, therefore, the first and the third term can be cancelled by proposing a J E square psi bar square, which takes this form. Okay. You just take this, okay, and you have to take a factor of half, because T0 will act on EA and EB. So, you will get a factor of 2 when T0 acts on EA and EB, because there are 2 EAs it will act on. Okay. So, you have to take this, you have to multiply by half and add it. Okay. Here you have to change the sign also, because T0 when since it is acting from here, it has to only go through 2 gravity nodes. So, there will be no change in sign. Okay. So, therefore, you have to change the sign. Okay. So, that is how you obtain the terms that will cancel this and this. Okay. But the second term will not cancel, because it does not have this form of EA times a torsion multiplied with an antisymmetric thing. Okay. So, the second term has to go to 0 on its own. Okay. So, that gives a constraint that this A, B, C, J, M, N, P, that was the thing that was appearing in the right supersymmetry transformation of sigma ijk, which was in the irrep 5 of SU2 and was self-dual in the Lorentz indices, that has to go to 0. Okay. So, whatever sigma ijk I propose, okay, the right supersymmetry transformation should have this constraint that this object has to be 0. It is I have not yet, I mean it is it was a chiral fermion. It had some chirality, right, that okay. So, it needs to have the chirality, because it is coming in this bilinear. So, this had chirality plus 1, right. So, this will also have chirality plus 1.
So, its next component would be some antisymmetric tensor, that you are saying.
Yeah, right. So, there were many terms in the right supersymmetry transformation of this sigma ijk, out of which I am saying that this has to vanish, this should not be there. Okay. Okay. Similarly, I think I will skip this. This will, you will get some other constraint coming from by looking at the other term in delta J, which has 1 Vl/2 right-handed gravity and 2 left-handed gravity. I will just mention the constraint. So, so this is the left supersymmetry transformation of sigma ijk. So, the left supersymmetry transformation of sigma ijk will break up into a Lorentz vector, which is in the irrep 5 of SU2 or irrep 3 of SU2. Okay, it is a Lorentz vector which can be decomposed into a irrep 5 of SU2 or irrep 3 of SU2. So, now this again this analysis tells you that this Lorentz vector, which is in the 5 of SU2, has to obey this constraint, okay, where this raising of indices basically means taking the complex conjugate. Okay. So, this so A B I J K L is nothing but equal to A B I J K L star. Okay. So, if you take the complex conjugate of A B L J M N, that has to be related to A B P Q R S in this fashion, okay, and there is a overall minus sign. So, it is pseudo imaginary. So, it is imaginary, it has some reality constraint, okay, but because of the presence of this Levi-Civita, it is pseudo imaginary. Okay. So, that is the constraint that you get on the block that appears in the left supersymmetry transformation of sigma ijk. Okay, and the other blocks that appear in the left supersymmetry transformation of sigma ijk, that comes in the next term in the action j. Okay, and then you have to now, I mean, these are the two layers, but then you have to complete these layers and finally find the full multiplet and how it transforms, and what are the constraints that it should have, and yeah. So finally, after obtaining all this thing, if you need to apply this density formula on some multiplet, you need to find a sigma ijk which has a right chiral weight, right Weil weight, right chirality, right S supersymmetry. It should be S invariant, and those constraints that we found, like AAB ijkl should be 0 and A ijkl should be pseudo imaginary. Those two constraints also has to be satisfied. Okay. And then once you obtain such a multiplet, then you just put it into this density formula and you have an invariant action. Okay. So what we did is we applied this to what we have worked out last year, which we call the real scalar multiplet. So it's a 24 plus 24 matter multiplet containing these fields, where these are the fermionic fields and these are the bosonic fields. Okay. And okay, so all the properties of these multiplets I have written in this table, and we also saw that this 24 plus 24 matter multiplet, if we impose certain constraint, okay, in general this Eij is a complex field. It's a complex field, but if I demand that this Eij is proportional to a real field times a phase factor, okay, then what I get is a restricted real scalar multiplet, and it's essentially become, I mean, I can have a one-to-map mapping between the tensor multiplet and this restricted real scalar multiplet. Okay. So that was what we obtained last year, and what we have found is that in terms of this real scalar multiplet, using the components of this real scalar multiplet, I can construct a sigma ijk which has all those properties that I mentioned earlier in my density formula. Okay. So this is just few terms. There are whole bunch of terms that I have not written down, okay, in terms of this real scalar multiplet, but this has a property that this has a required Weil weight, this has the required chiral weight, this is S invariant, and when you take the right supersymmetry transformation of this, the AAB ijkl term is not there, which means it is 0. Okay. So the AAB ijkl term is something that comes with the gamma AB epsilon L, and that is not there in the right supersymmetry transformation of this object, which means that it satisfies the first constraint. And if you take the left supersymmetry transformation of this object, you will find a vector A ijkl which is pseudo imaginary. That also, okay, it's a non-trivial thing, because what we essentially we write down some sigma ijk which is S invariant and has a right Weil weight and chiral weight, but it's not guaranteed that the other two constraints will be satisfied. But it turns out that it's satisfied, because and which means that this is the right thing to use, and so which means that the first block we obtain satisfies the required constraint, and then what we need to do is we just need to find the supersymmetry transformation of this, and the supersymmetry transformation of this thing appears in the other terms of the density formula, and then basically you have an invariant action for the real scalar multiplet. And because of this mapping of the tensor multiplet of the real scalar multiplet, you have an invariant action for the tensor multiplet. Okay, right. So this is what I mentioned here. Okay, so this is one way to obtain an invariant action for the tensor multiplet coupled to conformal supergravity. Okay, why is it interesting? Because this is not the action for the tensor multiplet coupled to conformal supergravity that we have obtained for the first time. Indeed, an action for the tensor multiplet coupled to conformal supergravity was obtained long back in '83 by David Philipp and Van Proyen in this paper called Improved Tensor Multiplet in n equal to supergravity. And this is going to be different action from that, because this action that they had obtained was based on a different density formula. So there is an invariant action that you can write down, which comes from coupling chiral multiplet and a vector chiral multiplet and a tensor multiplet. That is a density formula that they use, the invariant action between chiral multiplet and density and tensor multiplet. And then what they do is they use a gauge invariant object of tensor multiplet to write down a chiral multiplet. So, starting from the invariant action of chiral multiplet and tensor multiplet and writing down a chiral multiplet from tensor multiplet, they obtain an invariant action for tensor multiplet. But that had the property that the maximum number of gravitino in that action was 2, whereas what we have is maximum number of gravitino is 3. So, therefore, these two are indeed different action and not related to each other by some total derivatives or anything. Okay. So, that will be a different so that their action was also in invariant coupling with conformal supergravity, and that was used when one wanted to go from conformal supergravity to Poincare supergravity, where tensor multiplet is used as one of the compensator. Okay. Here we are proposing a different invariant action for tensor multiplet, and it will be useful to see what implications it has for going from conformal supergravity to Poincare supergravity, because tensor multiplet is one of the compensating multiplet in going from conformal gravity to Poincare gravity. So, that will be interesting to see. And another feature direction that we are looking at is n equal to 3 conformal supergravity. So, the while multiplet for this n equal to 3. So, n equal to 3 is an interesting theory, because without gravity you do not really have an n equal to 3 theory, because one can show that if you have n equal to 3 supersymmetry where with spin less than 2, then there is always a fourth supersymmetry. So, it becomes n equal to 4. But when you have spin 2, which is gravity, then you can have a manifest n equal to 3, which is not n equal to 4. And this was indeed exploited by these people, Van Moyden and Van Proyen, in getting the n equal to 3 while multiplet, and we would like to obtain the invariant action for n equal to 3 conformal supergravity, and also for n equal to 3 vector multiplet, and go from n equal to 3 conformal supergravity to n equal to 3 Poincare supergravity using this principle. Okay. So, sorry for the long talk. Thank you. If there are any questions, you can ask. Yeah.
Are there any applications at the level of conformal supergravity itself for reducing the Poincare supergravity?
Any applications at the level?
Are there any relevant calculations that one can do with the conformal supergravity action that you have obtained? All the black hole entropy calculations.
Right. Yes. So, you need of course, you need Poincare supergravity, yeah, which means you need not only action for the conformal supergravity, you also need action for the compensating multiplets. And yeah, so this formalism that I have talked about, this not only is useful for obtaining action for conformal supergravity, which means that you write down these composites in terms of the while multiplet fields, but you can also write down action for the compensating multiplets, where you write down these composites in terms of the matter multiplet fields which you are using as compensators. So, in our case we use this formalism to write down an action for the tensor multiplet coupled to conformal supergravity, which is one of the compensating multiplets. And since this is different from the one that was used earlier in the literature, so we would believe that this has some influence on the Poincare supergravity that one obtains, and we do not know what would that mean for the corresponding black hole entropy calculations and all, whether this would like vanish when you start using the entropy function formula or something, whether this will vanish or this will give some additional contributions, that we do not know. So, one has to see. Yeah.
Here this chiral multiplet is just a placeholder where you can put various
Exactly.
So, you can get any higher derivative corrections in principle using this.
Right. Yeah. So, in conformal supergravity, pure conformal supergravity is a four derivative term, right? But when you use vector multiplet coupled to conformal supergravity, you get a 2 derivative. But once you combine conformal supergravity action with the vector multiplet action, and you remove the auxiliary fields by using the equations of motion and gauge fix the additional symmetries, then you get a higher derivative theory. Yeah.
Gauss-Bonnet one of these, does it appear in
Yeah, Gauss-Bonnet invariant also one can construct in this way. It's a little tricky how to do that, but people have done it. I mean, when you write, if you just take vector multiplet coupled to conformal supergravity, and the conformal pure conformal supergravity action, the only thing that you're going to land up with a wild square term, right? But there are ways in which one can obtain the Gauss-Bonnet term. One can in fact obtain all curvature square invariant in Poincare supergravity starting from this. Yeah. I'm not so sure how one does using this standard Weil multiplet that I had discussed here, but using something called the Dilaton Weil multiplet there. But people have also done using the standard Weil multiplet. There is something called the Dilaton Weil multiplet also. It's a different version of Weil multiplet where Dilaton is one of the matter field that you need to add. Yeah. So yeah, using that I have seen how people have constructed all curvature square invariants in Poincare supergravity. Okay. Any question?